Most of us understand Newton's first law at this point, that an object in motion stays in motion unless acted on by a force. But there's another thing to consider about this. What does it mean to stay in motion? It doesn't just mean to keep moving. It means to keep moving at the velocity you have in the direction you were going. If you want to have somebody move in a different direction, you got to apply that outside force. And a really good example of this is turning. What if we wanted our person here, instead of moving straight, we wanted them to round a corner like that. I've drawn this new path as a circle, and I did that because that's the easiest type of cornering motion to understand. So we'll treat this as circular motion. So if the law of inertia, Newton's first law, says that our person should continue in this direction, we have to ask ourselves, what direction would a force have to be to get us to start moving in a circle? Well, notice that my white line has started to go below my yellow line. So here it's probably a downward force. Something like that. As we continue, though, now we're going a little more to the left than we'd expect if we were going to go in a straight line. So the force is turning a little more to the left. If we're going to go in a straight line here, we'd be shooting down the board, but we're turning to the left of that. And I think you can see that as I go around, the force needed to keep me moving in this circular path is an inward force. We call this type of force the centripetal force. And that's just Greek for center seeking. So what I'm going to do now is I'm going to run around a corner, and you're going to see that this inward force is absolutely necessary. I'm going to do it in a situation where I don't have enough of it, where there's not an inward force to help me turn. And I want you to predict what's going to happen. So the coefficient of friction between my shoes and the tile floor, it's pretty high. And as fast as I can run, the frictional force appears to still be enough to hold me in a turn as I'm going. So I taped some cardboard to my feet in order to decrease friction. And we'll see what happens. We'll pay special attention to the direction I go in as I try to round the corner. So I think it was pretty clear what happened when I didn't have enough of this inward or centripetal force. I kept flying outward. And sometimes people think that there's an outward force that's pulling them out as they try to round a corner. And they even make up a name for this. Sometimes they call it the centrifugal force, the center fleeing force. But that's not really what's going on. If I want to make this white curve, I have to consistently have this inward force. When the inward force is not enough, well, what am I? I'm an object in motion, and I want to stay in motion. So let's say I'm going fast enough here that I no longer can provide enough inward force to turn me. What do? And that's what you saw in the hallway as I went flying outward. From my perspective, it really felt like I was being pulled outward. But I think from the angle you guys were at, you could see that I just failed to make the turn. And it was my inertia, my momentum, the fact I was an object in motion, that's what kept me going. There was no outside force. Let's take another look at how friction can provide an inward or centripetal force that applies more probably to our everyday lives, and that is trying to make a turn as we're driving. This picture here on the lower right, this represents me on my way to school skating out on an icy morning when we didn't have a delay. You can see my car is proceeding on North Main Street. I was trying to turn onto Wadsworth, and that's always a pretty slippery place.
And I wanted to follow this purple path and have an inward frictional force. But the frictional force was not enough, so I was an object in motion and I stayed in motion. I didn't actually leave the road, but I started to drift outward. Again, that's not an outward pull, that's just me following my inertia. So here's another look at that car moving in a circular track. You can see its velocity is always tangent to the circle. And the inward force is caused by friction, like before. This tries to make the point, though, that if it's no longer going in the direction it was, if it's changing its velocity, there must be an acceleration. So that acceleration is something we're going to have to look at.
What we need to do next is we need to study what these inward forces are. And I think you saw from this video that the inward force for me was friction. These inward forces aren't some magical new force. They're always going to be something we've studied before.
So the big idea of these centripetal forces is that they're not anything new. They're all forces we already know. They just point in a particular direction. I'm going to start by talking about tension forces. So here's the force picture free body diagram for me swinging one of the Angry Bird stuffed animals along on a string. I want to use an example of something I'm sending in a roughly horizontal circle like this. It's not perfectly horizontal, but we're going to approximate it as such for now. So if we were going to look from the side, we have the force of gravity down and a tension force inward. That's going to mean it's not perfectly horizontal, but we're going to neglect the gravity for now, just to really focus on the force that's pointing in towards the center of the circle. So as you can see, there's an inward directed tension force, and it's the tension in the string. The bird will continue to move in a circle until that tension force goes away, like the string breaking or me letting go. So we'll come back and look at this situation in just a bit. But before we do that, I want to look at a couple other forces that can be used to provide a centripetal force and a centripetal acceleration. This is a beam of electrons moving through hydrogen gas, and you can see it's in a circle. The electrons are being tugged on individually by a magnetic force. Finally, gravity can cause circular motion. Here's an actual picture of the moon orbiting the Earth, and the inward force is supplied by gravity. It's strange to think of the motion of heavenly bodies as being similar to the motion of rounding a corner or swinging something on a string, but we can definitely approximate orbits as being nearly circular, and gravity provides that same inward force. So I hope at this point what you've seen is that if you're moving in a circle, you have an inward force, and as you continue to move around the circle, that force changes the direction it's pointing in, and it's causing an inward acceleration because force is directly proportional to acceleration, sigma F equals ma, so the acceleration will be in the same direction as the force. Without this force, objects would just continue in a straight line path. And if you're the object spinning, that feels like you're being pulled out. But if you're from the outside looking in, it's clear to move in a circle, objects need to be pulled in. In order to do some math problems that help us solve for information about circular motion, we really need to double down on what are these forces and what is this acceleration, and how can we use them with our Newton's second law equation, sigma F equals ma. So we're going to go back to the situation where I was swinging the Angry Bird. And again, we're going to neglect the force of gravity. We're just going to pretend this is a horizontal circle. And we're really going to look at it from a bird's eye view. And we're going to try to figure out how the acceleration of this object is related to the force pulling on it. Once you've got a force picture or a free body diagram just like what I had there, you write sigma F equals ma. And we've seen that we need to pay attention to what dimension forces are in. So up until now, we've used a set of axes like this, X and Y. The reason this is a little bit more challenging is that as this object changes its location, the direction of the tension force is going to change too. So we really don't have a fixed X and Y axis. It would almost be better if we could have an X and Y axis that rotated with the object, so that one of the two axes is always pointing inward, because that's what our tension force is always doing. It's always pointing inward. So we're going to call the axis we're paying attention to, instead of X or Y, we're going to call it R for radial or radius. And what we're going to do is we're going to look at forces along the radial axis. It's pretty easy in this problem. It's just Ft. As we've said, this acceleration is different than others we've seen so far. It's not causing it to speed up, it's causing it to turn. And we're going to call it the centripetal acceleration, which means inward acceleration. So typically, what we would have you do is we'd have you try to investigate some variables that might affect the centripetal acceleration. Students typically recognize that if I go faster, it tends to pull it harder. That's starting to hurt, actually. And they also recognize that if I have a big radius, which for the tension force is just the length of the string, I have one type of force. And if I have a smaller radius, that force changes too. So the two variables that affect centripetal acceleration for an object are velocity v and radius of the circle r. So I'm going to give you guys the equation for centripetal acceleration for now. As we've said, centripetal acceleration depends on velocity, but not just velocity, velocity squared. The faster you go, the acceleration actually increases quadratically. It's not linear. You go a little bit faster, you get a much more acceleration. And it's inversely dependent on the radius. So what can we do with this equation? Well, we can see our tension force equals m, and now we have an equation for AC. It's v squared over r. So the process of coming up with a sigma f equation involves identifying forces that act along the radius of the circle, listing them. In this case, there's just one force. And then plugging in v squared over r for acceleration. This is a good problem for trying to see how we can mathematically understand circular motion. So I have the Angry Bird. It's swinging around on a string like you saw before. I have the length of the string, and I have the speed. Let's try to figure out about forces on it. Here's our force picture, or free body diagram, and we can see we have an inward direction tension force. So you just do a sigma f equation. In our case, our only radial force is tension. The A is this new acceleration, so we can plug in and we can solve for how much tension has to be. So here's another problem that talks about the force of gravity between the Earth and the Sun as the Earth orbits. And you can see that it's really fundamentally the same. We only have one radial force here. It's not tension this time, it's gravity. But we still end up with the force equals mv squared over r. As long as there's only one radial force, almost all these problems look like this. So here's one involving the frictional force. Now, obviously this is sigma f, so if there was more than one force pointing in or possibly out, we would have to add them. But that'll be for a later lesson. If out of this video you got that objects moving in a circle have an inward force, that force is a real force like friction and tension, that we do sigma f equals a and put the real force for sigma f, and we put v squared over r for that inward acceleration. If you got those things out of this video, you're in great shape.